Okay, we're on to the last couple of new topics that we're going to cover during this class. And we're starting off with scatter plots and correlation. So let's talk for a bit about, switch, there we go. There we go. Okay, let's talk for a bit about scatter plots, what they are, and how to check for a correlation between two variables based on a scatter plot. So a scatter plot is a graph on the coordinate plane, so x-y axis, contains 1 point for each pair of data. So, for example, if we are, well, it needs to be numerical data on both cans, so the example of cat ownership doesn't really work well. So we've got one axis, horizontal first. The horizontal axis is one variable, the vertical axis is another. So we don't connect the plots on this. Hopefully we'll see one shortly. We choose which axis to put which variable on based on which one we think influences the other. So if we think a change in one variable causes a change in another, then we put that variable, the explanatory variable, the one that might cause a change in the other, on the x-axis, and the response variable on the y-axis. So if you remember from algebra, you usually write y equals some function of x. So this is what we expect to change something and what we expect to be changed. So this really does enable us, it lets us see trends in the data. Does it look like it's kind of a straight line? Does it look curved? Is there no pattern at all? How close to straight is it? Is it a positive slope? Is it a negative slope? Does it curve down? Does it concave down, concave up? Some weird thing like that. All sorts of things. So let's look at an example. If you have the quarterbacks from the 2011-2012 NFL season, or rather a selection of them, number of passing touchdowns, salary, and quarterback rating. I'm not sure who that's rating by. Oh, and there's a few more. Okay, so if we took these and we could look at, take that data to make a scatter plot, show the relationship between the base salary and the number of touchdowns the quarterback has thrown in one season. Okay, so which variable do we think is likely to be the one that influences? I would think that the more touchdowns they throw a season, the more they get paid. So I'd probably do touchdowns on the x-axis and base salary on the y-axis. All right, so if we plot that, so if we take this data and plot these points, so I'd plot 1 point at 46 and 3 million, 18 and 12.5 million, etc. And what we see is this. Doesn't really look like there's much of a trend. Maybe a slight downward straight line, maybe a little sine wavy thing, but it's there's not really much of a pattern evident. I mean, I could stretch and force myself to pick one out, but there's really not a pattern here. As they say, you don't see a linear pattern. You don't really see a pattern. You've got to really try hard to pick a pattern out of that. So it really indicates there's no relationship between those two variables. It's quick and easy to see that without having to spend a lot of time on the statistics. You just look and there's nothing there. So if we use that same table of data to show a scatter plot between the touchdown throws and the quarterback rating for that sample quarterbacks. Again, we would expect the number of touchdown throws to influence the touchdown ratings, because quarterback's rating, since touchdowns is one of the factors that goes into that. Um, so we'd probably put touchdowns on the x-axis and rating on the y-axis, and sure enough, there's a nice linear trend. The more touchdowns they get, the higher the rating is. So this is a positive slope, and yeah, that does look pretty linear. Linear pattern with positive slope. So if it follows roughly a straight line, it's a linear relationship. If it increases, the response variable increases as the effect variable increases, it's positive slope. So the combination is a positive linear relationship. The opposite, of course, is negative linear relationship. So there we go, positive slope, negative slope. All right, so let's look at another example. We've got a scatter plot. All right, so do we think that these variables would have a positive slope, negative slope, or be nonlinear? Number of hours you study for an exam and the score you make on the exam. First guess. Positive, negative, nonlinear. Those are your options. Okay? Second one. Price of a used car and the number of miles on the odometer. Positive relationship, negative relationship, or nonlinear. Pressure on the gas pedal and speed of the car. Positive, negative, nonlinear. Shoe size and IQ for adults. Positive, negative, or nonlinear. All right, take your best guesses and let's move on. So as the number of hours you study increases, the score you receive is usually higher. So we would expect a scatter plot to probably have a positive slope. That being said, I would think the time when you study matters more, because if you study really long the night before the exam and don't get enough rest, you're going to get a lower score, so you're probably better off not doing that. Study early, study often. Don't cram. Number of miles on the used car, as that goes up, usually price decreases, so we would expect a negative slope. The harder you push the gas pedal, the faster the car goes, so we'd expect a positive slope. We would not expect a relationship of any sort between IQ and shoe size, so we would expect we wouldn't expect to see a linear relationship. So possibilities, we could have a strong linear relationship, so it's a very tight grouping, not a lot of scatter. A weak linear relationship that's pretty scattered. If we we could maybe start picking out some other trends. Not really in this one. That's pretty obviously a straight line, but you could maybe pick out. There's maybe a couple of other trends you could pick out of there that might be possible. No linear relationship, really not a relationship at all. You could have a nonlinear relationship. In this case, it's parabolic. It could be a power law type thing or a logarithmic function as well. So we measure the strength of a linear relationship with the Pearson correlation coefficient. It's denoted by lowercase r. It's the value between -1 and 1. If it is positive, the scatter plot's got a positive slope, and the variables are said to have a positive linear relationship. If it's negative, it's got a negative slope, and the variables have a negative linear relationship. If r equals 0, then there is no linear relationship. Okay, r equals 1 is a perfect straight line with a positive slope. r equals -1 is a perfect straight line with a negative slope. If the values have a strong positive or negative relationship, we say they are correlated. The strength of that correlation is the absolute value of r. The larger the absolute value of r is, the stronger the correlation. All right, so we've got a perfect negative linear, perfect positive linear, no linear, strong relationship, weak relationship in here. Okay, so the Pearson coefficient is given by this equation. So we've got the number of data pairs times the sum of the product of the x and y value for each pair. So this is like, what was it? First quarterback was 46 touchdown passes and 3 million. So you multiply those. The next one was, I think, 10 touchdown passes and 12 million. Multiply those, add those together, do that for everyone. Subtract off the sum of the x values. Let's see, x was number of touchdown passes times the sum of the y values. Y was the salary, base salary. And divide that by the number of pairs times the sum of the square of the x values. So let's see, I'd take the 46 touchdown passes, square it, then the 10 touchdown passes, square it, add those together, do that for each one. Subtract off the sum of the x values and then square that sum. So it is important to catch where these parentheses are and where this exponent here is in relation to the parentheses and the summation. Right, so this is the sum of the x values squared. This is the square of the sum of the x values. Same thing over here with the y values. So this is a tedious calculation if you're doing it by hand. I would strongly suggest you do this electronically in some way. And that should be, yes, it is in your TI-8384. I don't know offhand if this is built into Excel. I've not used it there. I could build this pretty easily. Put the x values in one column, put the y values in one column, sum each column, sum the products of the columns. It'd be fairly simple to set this up in Excel. Right. So if we were to calculate the correlation coefficient for touchdowns and base salaries, all right, there's our data. Touchdowns and base salaries, and yes, I misremembered the second data point pretty badly, and that's okay. Don't need to remember that for the example to work. So take that, I can put it into the calculator. These steps should probably be fairly well known by now. I tell it I want to put these variables in these lists. Calculate min-reg ax plus b. So, okay, so it's using the linear regression, which is 12.2 is what when we talk about linear regression. And so we're telling it we're doing a linear regression. There's the ax plus b. Used to seeing it. Was used to seeing it in algebra as mx plus b. Slope, intercept. Press enter a couple of times. We would expect that to be close to 0. So we get the correlation coefficient here. The Pearson correlation coefficient is negative 0.251, which indicates a pretty weak relationship, if any. So if we do now touchdowns thrown and quarterback ratings, double check. Right, so now we've got this data. We again put these in we put our x value in L1, our y value in L2. Steps are the same. And we get a correlation coefficient of 0.925, which indicates a strong positive correlation between the variables. So the sample correlation coefficient is statistically significant if the absolute value of the correlation coefficient is greater than or equal to this critical correlation coefficient value. So there's a table of critical values in your book, table 1 in chapter 12. So at the 0.05 level of significance, let me grab my book here. I did not have that ready and prepared. Okay. Let's see. Oh, that is not a 1. That is an I. It's table I. Table I. Critical value. So this is table I in Appendix A. It is on page 933, and it looks like that. There are, I'm not sure how large that's going to show up. There are 3 columns. The first column is your number of pairs. Second column is for significance level of 0.05. The third column is the significance level of 0.01. So in this case, we had 10 quarterbacks we were looking at. So my critical value is 0.632. There. So if my Pearson's correlation coefficient is, the absolute value of it is greater than 0.632, then there is a statistically significant correlation between those two variables. Right, so in our first example, we had 0.251 for the absolute value. You remember it was a negative number, but absolute value, it's just distance from 0 we're interested in, which is less than 0.632, so that's not a statistically significant relationship. For the other side, we had a, what was it, 0.9 something for the correlation between touchdowns thrown and quarterback rating. So that would be a statistically significant relationship because that is greater than the 0.632. We can do hypothesis testing for this. We've got this, that looks like the Greek letter rho to me. We could say that rho equals 0, which implies there's no significant linear relationship, or rho is not equal to 0, which implies that there is a significant relationship. We could do this directionally. Greater than 0 applies a negative relationship. Less than 0 implies a negative relationship. Greater than 0 implies a positive relationship. The test statistic we need for this is T. We've got the Pearson's correlation coefficient, 1 minus that correlation coefficient squared, and number of pairs minus 2. Degrees of freedom is the number of pairs minus 2, and we're using the t-distribution for this. So we'll reject if the absolute value of t is outside of, we use the critical value of t. We'll reject based on these criteria, as we've done every other time we've used the t value for hypothesis testing. So if we're after a positive relationship, it's right-tailed. If we're after a negative relationship, it's left-tailed. If we just want to know whether or not there's a significant relationship, it's two-tailed. All right, so we're looking to see if there's a linear relationship between number of parking tickets and GPA during the same semester. We want to see if that's significant at the 0.05 level of significance. Here's our data. So let's look at the null and alternative hypotheses. Right, we want to claim that there is a significant relationship between the between the number of tickets a student receives and their GPA during that same semester. So the null hypothesis would be that there is no linear relationship, so or equals 0. I need to double check because this looks, that should be an R. That should be the correlation coefficient, I would think. No, they've got it. It's not just a font. Sorry, I thought it could have been a font mess up on the slides, but no, they've got it the same way in the book. I don't know what that R stands for, or sorry, rho stands for. It could be equal to 0, which implies a no significant relationship. If it's not equal to 0, it implies a significant relationship. So we want to, what we're trying to show is that there is a significant relationship. All right, so we want the t-test statistic. We want the 0.05 level of significance. So first we need to calculate the correlation coefficient. Easiest to do this electronically. We could argue that either variable affects the other, so they're just going to assign the number of tickets to the explanatory variable. Really, it honestly shouldn't matter too much one way or the other. And we get a negative 0.586. All right, rounding 0.587. And we've got n equals 15. They did round to 6 decimal places. I didn't read out all 6. They do that to avoid additional rounding error in the next set of calculations. So again, carry as many decimal places as you can until you're all done. So here's our t-statistic formula. We'll put that negative 0.587, 0.586619 in here, and 15 pairs in here, like so, and we get negative 2.612. So we need to draw a conclusion and interpret the decision. Right, we need first off the critical value of t, so we can set up the exclusion rejection region. Right, so degrees of freedom is n minus 2, so we have 13 degrees of freedom. We are doing a two-tailed test because we want it to be, that's what we're checking. We get, if we look that up, we get 2.16 is the critical value. Right, so if we can reject the null hypothesis if the absolute value of our test statistic is greater than or equal to 2.16. We could calculated 2.612. So it does fall into the rejection region, and we can reject the null hypothesis, so there's sufficient evidence to support a claim that there's a significant linear relationship between number of parking tickets a student receives, and the GPA during the same semester. Okay, so if we wanted to research the effectiveness of mail-out catalogs, they've collected data from the retailer's 8 largest markets with respect to the number of catalogs, and so this is thousands of catalogs sent out, versus sales in thousands of dollars. So this is 126,000 for 2,000 catalogs, and these are their results. All right, and there are 8 data points there, one data point for each market they were looking at. Again, they're just looking to see if there is a statistically significant linear relationship, not saying it's positive or negative, just whether or not it's there. And they're looking for this at the 0.01 level of significance. So, null and alternative hypothesis. Again, we're going to use the same ones we had last time. We're researching whether or not there is the relationship. Null hypothesis is that there is not one. Okay, so we're going to use the t-statistic, and the level of significance was 0.01. We'll need to calculate the correlation coefficient, and for that, so again, we will do this electronically. The explanatory variable in this case is the number of catalogs. They're wanting to see if number of catalogs, ideally they're wanting to see if number of catalogs affects sales. And it is starting to storm out there, so that is somewhat distracting. Sorry. So if we enter this into the calculator and hit enter a couple of times, we get this. What we have is a 0.504505. I'm going to stop there. 8 samples. So our correlation coefficient is 0.504505. Again, they've kept extra decimal places to avoid rounding error in this next calculation. We want the t-statistic. We're using this formula again. We've got our correlation coefficient and number of samples, and we get 1.431. Okay, so we are going to need to know what that critical t value is so we can come up with our rejection region. So 1.431. We're doing a two-tailed, so we've got half the tail out on each side. So we can look that up in the table. We get 3.707. We'll reject the null hypothesis if the absolute value of t is greater than 3.707. We had 1.431, so that's less than 3.707, and so we cannot reject the null hypothesis. There's not enough evidence to claim that there's a significant linear relationship between catalog distribution and sales in an area. Here we get to I would hope you've all heard this before. Correlation does not necessarily imply causation. Just because there is a statistically significant relationship between two variables does not mean that a change in one variable necessarily causes a change in the other. The world can be more complicated. Ice cream sales do not cause hot days. Hot days might cause ice cream sales. Let's go, no. Ice cream sales do not cause murders, I think is the one of the classic examples. There's higher ice cream sales on hotter days. I think there's higher murder rates on hotter days. So if we look at just the murder rates and the ice cream sales, it could look like I could argue that murders cause ice cream sales or ice cream sales cause murders. That is not the case. So if we've got a statistically significant correlation, there could be at least 4 things going on. Right? One variable could cause the other variable could cause one. Like if X was ice cream sales and Y was daily temperature, I would be very incorrect to say that ice cream sales caused higher temperatures. However, higher temperatures causing ice cream sales would make sense. We can also have one variable influences another, but both are also influenced by a third, right? Or we could have neither variable influences the other, but both are influenced by a third. So, ice cream sales and murder rates could both be influenced by high temperatures. I don't have a good example for this middle one right offhand. So we've got to be very careful interpreting the significance of correlation. Just because the correlation exists does not imply that there is a causal relationship between the two variables. It is natural to assume that one variable causes the other. It might make more sense to reverse the variables. It could be a combination of things. Yeah. It is more complicated. It is very important to remember that correlation does not imply causation. Just because something is correlated does not mean one caused the other, either direction. It's possible, but it doesn't mean that. It takes more work to figure that out. Okay, so the next thing we want to talk about is the coefficient of determination. It's a measure of the amount of variation in the response variable that can be associated with variation in the explanatory variable. So if the correlation coefficient is 0.65, how much of the variation in house prices can be associated with variation in number of rooms per house? If we're looking at rooms and price. Right? So the coefficient of determination tells us that variation. And the coefficient of determination is the square of the correlation coefficient. So 0.65 squared, we get 0.4225. So 42.3%, rounding up slightly, of the variation in house prices can be associated with the variation in the number of rooms in the houses. All right.